Welcome to our presentation, ArtiBoost, boosting articulated 3D hand object pose estimation via online exploration and synthesis. The presenter's name is Lixin Yang from Shanghai Jiaotong University. ArtiBoost is designed for tackling the task of hand object pose estimation. Given an RGB image observing the hand manipulating object, we want to design algorithms that can recover the 3D skeleton or the mesh surface of hand and the 6D pose of the objects, both in the same coordinate system. There are a lot of researchers has pushed the frontier of hand object pose estimation. Their methods follow the paradigm in the figure below, but with different network design and with different output representation. However, ArtiBoost is not motivated from creating another sophisticated CNN model, but rather to improve current tasks from the data perspective.
I will first introduce what inspires and motivates us to propose ArtiBoost. The pose estimation is usually defined in a bounded space. Take a classical articulated body, the robot arm, as example. All the pose configuration is defined in its configuration space, and this Z-space is unique, concise, and can be parameterized. Hence, in the pose estimation task, before we train the neural network to feed underlying data distribution, we have already known it.
Hand pose has its Z-space too. The compositional multi-body articulation, for example, the hand and object poses during interaction. If we limited the object types, we can also create a discrete Z-space to cover all the possible configurations. If we train a neural network with sufficient data, sufficient to cover all the possible poses in the Z-space, the network is able to reconstruct the underlying Z-space. As for the image-based pose estimation, it has an extra viewpoint dimension. Hence, the solution lies in a configuration plus viewpoint space, as we call it CV space. We start from a free-moved hand's articulation model. If we perform the discretion on joint's rotation angle with respect to the anatomically aligned axis, we can theoretically cover all the valid hand poses and the viewpoints, of course. For generating composited hand object pose, we follow the conclusion from several previous methods that enforcing contact can help us optimize a cross grasp. We start from an existing grasp, mimicking the canonical grasping poses of a simple parallel gripper, and randomly move the wrist around the offset surface of the object. At each wrist location, we assign a contact visible region on the object surface for each fingers. Finally, we optimize the grasp by minimizing the displacement between fingers and the contact regions.
To put the object, grasping pose, and the viewpoint direction together, we propose the concept of the CCV space, stand for the composite hand object configuration and viewpoint. However, learning on the vast amount of poses is ineffective. For example, similar poses may have already been observed multiple times, and those easily discernible samples may have a frequent appearance.
That is because, based on the uniform data sampling strategy, those hard examples with less amount will have a lower sampling probability and has a lower occurrence rate. Hence, they will be outweighed by other easily discernible training data. We design a mechanism that can adaptively sample the unbalanced data. We update the sampling probability from the inverse proportion to current model's performance. Thus, we can enrich those hard discernible samples and further boost network's performance. To put all this in a training pipeline, we implement ArtiBoost as a data loader. We start from a real-world source dataset, along with a sampling weight map that stores the indices and the sampling weights of the pose in the CCV space. During training, the sampled poses are rendered as RGB images in a parallel rendering pipeline. The rendered images are then blended into the real-world data as a mixed batch. The mixed batch are passed to the neural network. The loss of the network's prediction are then fed back to the ArtiBoost loader. The ArtiBoost loader performs mining and reweighting. The updated weight map replaces the current weight map and continue next epoch of training. As ArtiBoost is implemented as a data loader, it can be plugged into any sophisticated neural network model. We adopt two different neural networks models. One predicts the joint's 3D heat maps, and the other regress the manual's pose and shape parameters. We choose two datasets, HO3D and DEX-VCB, to evaluate the classification and regression models trained with our ArtiBoost. We compared with three recent methods. The tables show that ArtiBoost indeed made a significant improvement to the hope task. We show some qualitative results on the HO3D and DEX-VCB testing set. Current ArtiBoost has limitations. First, we do not explicitly mitigate the domain gap between the synthetic and real data. Second, as the render in ArtiBoost is not differentiable, current ArtiBoost only support exploration in a predefined lookup table, for example, the CCV space. We will leave the limitation for the future works. Thanks for your listening.